So, welcome to NPTEL Environmental Chemistry Problem Solving Session. Excuse me, yeah. So, this is week 8. I am Mansi Tripathi. I am research scholar at IIT Madras. I'll give you some example problems that you can use to solve the problems that are given in assignments, as well as this will help you in the examination if you have registered for that. So the question number 1 is, complexation generally increases the total concentration of metal ion in the solution. We need to find the correct statement. Okay, so there is the possibility that more than one statement is correct, and the marks will be only awarded when you can identify all the correct statements. So please go through each of the statements very properly so that you can identify the correct solution. The extent to which calcium ion can be removed by lime softening to form calcium carbonate may be limited in part by soluble complexation of calcium ion. Option C is, complexation decreases the toxicity of metal ions whose predominant toxic species is the free metal ion. In the COD test, mercuric salt is added, otherwise COD obtained will be underestimated. So in the COD test, we need many salts. So mercuric salt is also added. Okay, so we need to find out if it otherwise if it is not added, then COD will be underestimated or overestimated. Option A is, during hardness testing we add EDTA. Okay, which allows magnesium metal ions to be free so as to give a true endpoint of titration. This is for the hardness test. So the correct option is A, B and C. We'll see how. So the first option was that complexation generally increases the total concentration of metals ions in the solution. So the explanation is, the complexation will lead to the reduction in the chance of precipitation. What happens? I'll change the pen color. What happened? There are many cations which are there in the solution, like calcium. So after the solubility Ksp, they should be precipitated in the form of CaCO3. But when they form complexes with other anions or cations, then what happened? They won't precipitate. Therefore, we say that they increases the concentration of metal ions in the solution, because they should precipitate if we are providing some environment for them to precipitate. But still everything is there, but still they are not precipitating. Then what can be the reason? Because they are not precipitating, we are doing everything which will make them precipitate. We are adjusting the pH properly, we are adjusting the temperature and everything. They should precipitate, but still there is no precipitation. Then we say that there is complexation. These ions are forming complex, which is preventing them from precipitation. So that is why option A is correct, because complexation generally increases the total concentration of metal ions in the solution. Since they are not precipitating, they are still in the solution form. It means it is increasing the concentration. Option B is, the extent to which calcium can be removed by lime softening to form calcium carbonate. How is something is removed from the system? Either if it is in form of gas, it is evaporated. If it is in form of cations or anions, we try to precipitate it. So calcium carbonate is the form, which S also indicates the same. Okay, this says that it is in solid form. It means it is precipitating. However, it is limited by the soluble complexes of calcium. Okay, like option 1, here may also be the formation of complexes of calcium. So what is the explanation? Due to soluble complexes of calcium, the amount of free calcium in the system will be less. Okay, amount of free calcium is less. So CuCO3 solid is breaking into Ca2 plus and CO3 2 negative, and this is the KSP. And the reduced amount of calcium in the system will reduce the reaction coefficient K, and hence the extent of precipitation will reduce. So what is happening? When this calcium is forming complex, it means this calcium is going out of the system. Okay, so because the product is reducing, what will happen with the Le-Chatelet's principle? This calcium carbonate will be converted to calcium ion and carbonate ion. In that case, what happens? More calcium carbonate solid will be dissolved. Hence, precipitate will be very less. Okay, what is happening? I'll repeat again. Because this calcium is forming complex, so it is going out of the system, due to which the reaction is moving in the forward direction. So more calcium carbonate is being dissolved rather than being precipitated. That's why the removal is difficult. Option C is complexation decreases the toxicity of metal ions whose predominant toxic species is the free metal ion. So what is the toxic species? It is the free metal ion which is toxic. However, when those are forming complexes, they are no more toxic, because we say we have considered, like, let's talk about chromium. Chromium 6 plus. Chromium 6 plus is toxic. However, when this chromium is forming complex, okay, I'll write complex because this can be any type of complex. It can be with water or anything. So this is toxic. However, when it is forming complex, it is less toxic. So we can say that complexation is a good thing here. It is reducing the toxicity of chromium. However, it is creating difficulty in removal of chromium ion from the solution. Okay, but it is decreasing the toxicity because chromium is not free anymore. Option D is, in the COD test we add Hg salt, mercury salt, otherwise COD will be underestimated. Let's see the explanation, because this was a wrong statement. COD will be overestimated. How? In the COD test, mercuric salt is added to oxidize the available chlorine in the solution. Okay, so we add Hg to oxidize the available chlorine. Otherwise, if we are not oxidizing the chlorine, what will happen? The oxidizing agent that we are adding, K2Cr2O7 and concentrated H2SO4, they will be consumed in oxidizing chlorine ion also. Hence, okay, see, there are many, like we have organic matter inside our sample which needs to be oxidized. We have chlorine also, and we can have other ions also. So, what is the COD? COD means the amount of oxygen required to oxidize the organic matter. This is the real COD. So, what will happen if we will add K2Cr2O7 and H2SO4? This will oxidize both the things, right? So, we will think everything is organic matter, but no, chlorine is not organic matter. So, to oxidize that, we add Hg. We add Hg. So, whatever the remaining thing is there, K2Cr2O7 will be used in consuming that. So, we will know the real amount of COD. Otherwise, for both the things, it will be required. K2Cr2O7 will be required. So, it will lead to overestimation of COD. We will think more organic matter is there, but in reality, it is not. It is organic matter plus chlorine plus other compounds. Okay. Option A is, during hardness testing, we add EDTA. which allows magnesium ion to be free so as to give the true endpoint of the titration. Okay, we add EDTA. Why? According to this statement, why we add EDTA? To allow magnesium ion to be free so as to give true endpoint of the titration. But actually what is happening? While testing for hardness, we first add EBT, that is erythrome black tea, which form complex with Mg2+. So what is first reaction? Mg is there. We add EBT, erythrome black tea. This is indicator. Okay, this leads to the formation of complex. Okay, then this thing is titrated with EDTA. Okay, EDTA is the thing that we fill in burette. This is our titrant. So first, in a flask, in a conical flask, our sample is taken which contains Mg2+. In this we add EBT. Okay, so here a complex is formed which is magnesium EBT complex. On titrating this complex with EDTA, blue colors appears. It what happens? It replaces, because EDTA is stronger, so it replaces EBT and it forms magnesium EDTA complex. Okay, so what is happening? First magnesium is there, we add EBT, it forms Mg EBT complex. Then we started adding EDTA because EDTA is a strong complexing agent than EBT. So it is replacing EBT and forming Mg EDTA complex. So what is the amount, what is hardness actually? It is the amount of magnesium or calcium ion. Okay. So the amount of EDTA consumed, because it is forming complex, so amount of EDTA consumed will be equal to amount of magnesium ions. Okay, rest of the things will give color. You understood? So rest of the things will give color. That is why the amount of EDTA consumed will be equal to amount of Mg2+ ions in terms of EDTA. So there is an equation which we use to convert. So we can get everything in form of hardness, in the form of hardness in CaCO3 milligrams per liter. So why we are adding EDTA? Not to free Mg, but to make complex. Here it is written we add EDTA to free Mg, right? So no, we add EDTA to form complex. We add EDTA to form complex, not to free it. That is why I add EDTA. So question number 2 is, we have to use visual Mintek for this question. Use visual Mintek to determine the dominant species of cadmium in the seawater. Okay. Assume that total cadmium is 4 microgram per liter and that the ionic strength is 0.7. Total strength we know ionic strength, and consider OH, chlorine, bicarbonate, carbonate and sulfate as possible complexing ligands. Use the concentration of these ligands given in table below. The dominant dissolved series species will be, we need to find out dominant species. So please try to solve this question. We'll see the solution in a minute. We'll see the solution now. So the solution is the dominant species will be cadmium dichloride. How? Let's see. We will put in visual Mintek. Calcium we are putting because it was given 4 microgram per liter. Please have a look at the unit properly. It's 4 microgram per liter. So that is why 4 into 10 raised to power minus 3 milligrams per liter. Ionic strength is 0.7 molar. pH is given as 7.9. Sulfate, chlorine, alkalinity, everything is given. Okay. Then we will put everything. Okay. Here. Then we will run Mintek and click on the button view species distribution. So this is what we got. The species distribution. So as we can see, the dominant species is, for we're talking about cadmium, right? So we will see this column only. We will leave every other column. And we are saying the dominant species is CdCl2. Okay. The other dominant species is CdCl plus. So this is the first and this is the second. Rest are very less. Okay. This is third. This is how we will solve this question using visual Mintek. This will make our work really easy. Now talking about question number 3. The owner of the industry that generates wastewater containing both Ag and Hg, silver and Hg, both are there. Considering, now it is considering 2 options for discharge. So one option will be ocean and the other will be river. Okay. One option is to discharge the water through the ocean outfall, in which the initial dilution is predicted to yield concentration of 0.04 milligram per liter of total Hg and 2.5 milligram per liter of total Ag. So one is ocean outfall and the other is river discharge. The second option is to discharge it's written the alternative discharge to the large river, in which the dilution would be faster. In the river, dilution is faster because less ions are there and more extensive. So the total concentration of the metal near the outfall would be lower by 10 to that of yielded by ocean outfall. Okay, you understood? In ocean, it's 0.04 milligram per liter to 2.5 milligram per liter, but in river, it will be lower by the factor of 10. It means 0.004 milligram per liter or 0.25 milligram per liter. Okay, so the major complexing ligands in the 2 potential receiving water are chlorine. And how much chlorine is there in ocean? 19,400 milligram per liter, and in river it's 35 milligram per liter. So we have seen that there are chlorine as well as sulfate. Please, it is written, okay, 0.04 will be in ocean and in river it will be divided by 10. But we have to look into complex formation also, because formation of complex in most of the cases reduces the toxicity. Okay, so that's why we have to look into complex formation, and it is kind of visible that more complex will be formed in case of ocean because of more sulfate as well as more chloride. So we have to solve everything very properly. So the other things are that both the solutions are at pH 8 and the ionic strength are 0.62 molar in ocean and zero point zero 0.01 molar in the river. The suitable option would you recommend to minimize toxicity? We are talking about minimizing the toxicity. We are not talking about just minimizing the concentration. We are here to minimize the toxicity. That's why you have to look into concentration. That's point number one. And the second, complexation. Okay, please try to solve this question. We'll see the solution in a minute. We'll see the solution now. So the option is ocean outfall, as I have hinted. This is based on the toxicity, which is reducing because of the formation of complex. But we'll see how. So this question is also solved in Visual Mintek. So we will do it step by step. First we'll do for ocean, then we will do for river, then we will compare. So for ocean outfall, we have Ag values, Hg values, sulfate and chloride. Okay, we have pH, ionic strength, everything. So that is what we are putting here. Then we will concentration of is negligible as compared to complexes. Okay, as we can see, complexes when we are comparing it with the complex, this is the concentration is negligible. Okay, then we will view species distribution, and what we found that percentage of total concentration of free ions is very less as compared to complex, and mostly complexes is predominating in case of ocean. And as I've told you, when it leads to complex formation, the toxicity reduces because the free ions are more toxic. Ag plus and Hg plus, Hg2 plus are toxic as a free ion. So this is one thing. We have seen Ag plus is 0.95, AgCl, AgCl2, and this is the distribution. Okay. Now we will see about river. For river, dilution factor is 10. So as I've told, 2.5 is 0.25 and 0.04 was 0.004. Sulfate, chloride, everything we have. We are putting it in the list, as you can see. Then we will check the view species distribution. And this is the species distribution we can see. So here we are seeing that Ag plus is high, 36 percentage distribution, and complex are also there. Okay, so percentage of total concentration of Hg is less, but Ag is 36%. So it will render high toxicity. So that is why the discharging wastewater in the river is not suitable option. That is why we are discharging it in ocean, because most of the complex are there in ocean, and in if we are discharging just mercury, then it's fine for river also. But since silver is also there and 36% is in form of Ag plus, which is toxic, so that's why we are discharging in ocean. Coming to question number 4, a solution is prepared by adding aluminum fluoride in distilled water. The concentration is 0.01 molar. If H plus F negative AlOH3 are selected as components, then which equation gives below are correct? We have to consider that no precipitation is forming. Okay, please try to solve this question. We'll see the solution in a minute. So option A and C are correct. Okay. So we can calculate total H plus and total aluminum. So these are the correct options. So the components were these, and these were the species which can be used to form the components. Now there are different species. First is H plus, only H plus is required. For H2, for making OH, H2 minus H is enough. For making Al3 plus, this is the equation, AlOH3 plus 3H minus 3H2. For making, by using these three components, we have to make all the species, right? So how many species are there? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So 8 species are there. That's why we have 8 formation equation by using just 3 components and 1 H2. So these components will be enough to make all these species. So you can see all the species are prepared by using these components plus H2O or subtracting H2O. So this is the formation table. We are using just 3 components to make all these species. Huh? So by checking how much H plus is there, just by multiplying H plus into 1, OH into minus 1, Al3 plus into 3, huh? AlOH2 plus into 2. You can see here. Similarly, we are making for Alt plus also. Okay. So these equations are enough for forming these things. So question number 5 is, a solution is prepared by adding aluminum fluoride 0.1 molar in distilled water. Same question. Predominant aluminum species at pH 3, 7 and 10 at equilibrium are what? So at different pH, different species will be there. You can use visual Mintek also, and you can use the diagram also. Please try to find answer of this question. We'll see the solution in a while. We'll see the solution now. So the correct option is option A. At pH 3 it will be AlF3. At pH 7 also AlF3, and at pH 10 is AlOH4. How? We'll use visual Mentec to find out that. So first we have to add 0.1 molar of Al and F 0.3 molar. So AlF3, right? So when we write the equation, what will happen? Al F3. When it dissociates, what will happen? Al will be formed plus 3F are also forming. So that is why this was 0.1 molar, right? So this will be also be 0.1 because the coefficient is 1, and here this will be 0.3. So this is what we are writing here. Aluminium will be 0.1 and this will be 0.3. Okay, so then we will fix the pH as 3 because 3 different pH we have to check. So we'll fix the pH as 0.3. Now we will run the visual Mintic and click on species distribution. What we can see is 67% is AlF3. So at pH 3, AlF3 is the dominant species. Going to the next pH, we will fix the pH as 7, and what do we see is AlF3 is the dominant species at pH 7 also. Now we'll fix the pH as 10. And on clicking view species distribution, what we found that AlOH 4 negative is the dominant species, 81%. So dominant species is AlOH 43. So that's why at 3 and 7 AlF3, and at pH 10 AlOH 4 is the dominant species. So that's what we will mention. Question number 6 is, a solution is prepared by adding AlCl3 at 0.01 molar into distilled water. pH can be adjusted by adding NaOH and HCl into the solution. The pH at which AlOH3 will start to precipitate is, so there will be different regions of pH where it will start precipitating. So we need to find out the pH where it will start precipitating. Okay, we can see that this has a solubility. The solubility is least at what pH? So there will be different complex formation. You might have studied this thing. So at what pH the solubility will be least? So this is what we need to find out. So please try to solve this question. We'll see the solution in a while. I hope you have solved this question. You can match your question with the solution. So the answer will be that at pH 4.8 it will start precipitating. Okay, so this pH is 4.8. And how we got to this pH, we'll check. Not 48, it's 4.8. So first we have to add the components. See AlCl3. So this is the components that we are adding. Click on solid phase and excluded species menu and click specify possible solid phases. We need to specify the solid phases and we will click this as the solid phase. So there will be many solid phases coming or when we will click on this menu, but we have to choose this. Okay, we know we can see the log Ks value. The solubility is, we need to find out where the solubility is least. So click on multi-problem or sweep menu and select sweep. One parameter is varied option and add other things as shown below. Okay, this pH, we will add other components, type is concentration. So these are the different things that we will add. The common complexes we will select. Okay, these are important. So we will run Visual Mintech and select the sweep result. So this is the menu that we will get. And so at the pH of, while doing trial and error, we will find out that the pH of 4.8 aluminum hydroxide start to precipitate. So the answer is pH 4.8. So we have started the pH value from 1, then we are incrementing it as 0.2. Okay, so we are varying just one parameter, that's why we are clicking here, because what is the parameter that we are varying is it's pH. So it is like 1 point, then 1.2, 1.4, 1.6. Then when it got to pH 4.8, we will be able to see that AlOH3 is precipitating the most. Okay, this is how we can check. So this thing can be easily done in Visual Mintech. The next question is, a solution is prepared by adding AlCl3 at zero point 0.1 molar into distilled water. Then out of all these things, the dominant species at pH 3, 5 and 11 at equilibrium are. Similar question. Please try to solve this by yourself. Then we'll see the solution in a while. We'll see the solution now. So the option D is correct, that aluminum AlOH3 in form of amorphous salt and AlOH 4 negative are the solution present as pH 3, 5 and 11 respectively. We'll see how this is happening. So this is the diagram, solubility versus pH. So we have to follow the answer of question number 10 up to point 4. Follow the answer of question, not 10, I'll correct it, up to point 4 and print the data to Excel by clicking print to Excel. Then we will prepare log C versus pH graph for all the concentration. It can be seen that at pH 3, dominant species, okay, at pH 5, we can see the dominant species, pH 11, respectively, are Al3 plus. These are the dominant species. So that's all for today. I'll share the slides with you all. So I will close for now. I'll share the slides with you. And in case of any doubts, you can ask me in the next session.
Okay, thank you, madam.
Thank you so much.